Well, let's talk about error when we deal with matrices and system of equations and vectors. Now you recall that when we have just a simple number, a real number, then the error is defined as the absolute value of the approximate solution minus the exact solution. So for example, if the exact solution is 2 and the approximate solution is 2.01, then the error, in this case, this is actually absolute error. So the absolute error is 0.01. The relative error is the absolute error divided by the exact solution, or the exact value. So that gives us 0.5%. Now for system of equations, then the exact solution could be a vector, two components, if you have two variables x and y, or if you have a system, let's say a 4x4 system, then your x vector would be x1, x2, x3, and x4. So if that's the exact value, when you solve a system, you may have an approximation of that solution, that exact solution. And then the error is calculated this way. We use something called norm. So the name of this operation here, this symbol is called the norm. That's a norm. Now there are several types of norm. This norm is called the Euclidean norm. Euclidean because this reminds us of a distance between 2 points, right? It's the Euclidean geometry. In the textbook, you will see different types of norm, and in special, you will see something called the infinite norm. So the infinite norm of a vector x is basically the maximum value, the maximum absolute value of the components of the vector. So we can write as maximum of the xi's. Okay. So, and to differentiate between the Euclidean norm and the infinite norm, we put an infinite right there. So example. So if you have x as a vector, let's say 2, 3, 5, okay? Or if you want to write that in an octave format, 2, 3, 5, okay? Then the Euclidean norm would be square root of 2 squared plus 3 squared plus 5 squared. And that's square root of 38. And that's about, let's see here, I have that in the calculator, yeah, about 6.16 maybe. And if we use the infinite norm, then this would be the maximum of these three values. Which is 5. Okay. So the infinite norm is easy to compute. Now the norms are different, the values that you get are different. But that's okay, that's how we define the infinite norm. And then just to illustrate the Euclidean norm, so here's the exact solution, 2, 3, and then here's an approximate solution. So the absolute error, well, we don't call absolute error because we don't use absolute values anymore. It's simply error. The error, it's the norm of the difference of these two vectors. So we subtract these two vectors, so 2.1 minus 2, and then we square that. 2.9 minus 3, we square that. That gives us this value. Okay, before I talk, now let's relate that to systems, but before I relate that to systems, let me show that how that works in Octave. So if I have a vector, let me go back here and use this example right here. if x is 2, 3, and 5. I'm putting in this semicolon here, so I want the vector to look like a column matrix. Then there's a command in Octave called norm. If I put norm of A, that gives you 6.1644. That's the Euclidean norm. If you don't say anything to Octave, then the norm is Euclidean norm. But if you want the infinite norm, then you can put x, comma, I, and f. That will tell Octave that you want to use the infinite norm, which is 5. Okay. Now, the error is useful. This definition of error is useful because you want to check your solution. Once you solve a system, you want to check whether that approximate solution that you get is okay or not. And you need the error. So there are two ways to compute the error. One, the simplest format would be to look at the original equation, matrix equation, and subtract both sides of the equation. So we move b to the other side, you subtract these two. So this should be approximately 0. Okay, the 0 vector here. And that's the error that we use. So that's how we compute the error. Here's an example. Okay, so let's solve this using the Gaussian elimination. So I'm going to put that over here. And move this system over here so we can see it. Alright, let's type the matrix A. Now notice that this matrix A is 10 to the negative 15. And then 1, semicolon, 1, 2. Okay. So 10 to the negative 15, which is right here. And here is 1, here's 1, and here's 2. The right hand side, 3, 5. Let's call GE and solve that system. And so x equals to GE A, comma B. Alright, we got that. That's why I have this solution here, negative 0.888 and 3. Well, now, is this a solution of the equation? How do we know? How do we compute the error, or how close this is to the true solution? Well, we can use a norm. So here is how we compute the error. It's simply doing A times x minus b. And I forgot to do, let's see, what if... Oh yes, okay, this is a good time to talk about this vector x. Look at x. X is not a column. Is not a column matrix. And in fact, this is a good time to change the way that the Gaussian elimination shows or returns the value of x. So let's go back here to the Gaussian elimination. Let me get that here. See, when Gaussian elimination solves, does the elimination, does the backward substitution, then the function returns x, but it returns x in this format. We want x to look like a column vector. So one easy way to do that is to do x equals to x and then apostrophe. The apostrophe here means it's a transpose. So for example here, x, if I put x apostrophe, that's x transpose. The transpose of a matrix, you're flipping the matrix. Everything that is column becomes row, and everything that is row becomes column. So that's the only thing we need to add here. So I'll put a semicolon there. So let me save that. So from now on, we're going to make sure that if the solution of a system is returned, we need to put that in a column format, a column matrix format. So let's call G again here. See, now x is a column matrix. All right, A times x minus b. So notice that the solution x is not quite a good solution, because if it was a solution, right? If the vector x was a good solution, exact solution, then when we multiply a times x and we subtracted b, we would get a column with zeros. And we don't get that. We get 0 and then 0.11. So this solution here that we got, not a very good one. So let's calculate the error. That's norm a times b, a times x minus b. And that's the Euclidean norm. So it's 0.11182. If you want to use the infinity norm, it's the same thing in this case. That's because one of the coefficients, one of the entries is 0, so they will look like the same. So the error is, see, the error is not quite small. It's 0.11. Right? It's far away from 0. Usually the error that we want are very, very small, like 10 to the negative 6 or 10 to the negative 9. But here it's kind of big. And that shows that this solution is not a very good solution. And this is due to several problems. Perhaps there is a rounding error, or the floating point format cannot handle some of the numbers that come up during the elimination process. So we will deal with that later then.